Hi, everyone. Thank you for joining the Protocol Labs Research Seminar Series. Today's speaker is Sebastian Henningsen. Sebastian is a PhD student at Humboldt-Universität zu Berlin and researcher at the Weizenbaum Institute for the Networked Society. He's going to talk today about mapping the interplanetary file system. Sebastian, I'll let you take it from there.
Thank you very much. So thank you for the opportunity to present our work here. My name, as you said, is Sebastian. I'm the first Sebastian in the list of authors here in this presentation. And I would like to talk about first the paper that we published at IFIT Networking this year about mapping IPFS, but also more recent works, as I've said in the intro already, that has been going on in the master thesis of Leo, who's also attending this talk today. Just a quick note on who we are. We are from the Weizenbaum Institute for the Networked Society. And that institute has the goal to basically research digitalization and society, how the first affects the latter and the other way around. So for example, through regulation of technologies and so on. We are in Berlin since September 2017, officially founded, so quite new institute and still in the process of finding ourselves, I would say. The most important part is that we are publicly funded, so we are impartial, and that is basically one of our main contributions, so to say, because we are there to, among other things, give consulting to the German government. And then you, of course, don't want to have any lobby interests and conflict of interest in general. We are interdisciplinary, which is kind of unique and quite a fun place to work. So as you can see in this pie chart here, there are only quite a few computer scientists indicated by these chips, quite a few lawyers, social scientists, communication scientists, and so on. So it's quite a diverse group of people and very interesting place to work. We as a group are only one of 21 other research groups. And if you want to follow our updates, not only on IPFS, but also other stuff that we're doing, please follow us on Twitter, JWE for Trust in Distributed Environments. We are 5 people that are full-time there, full-time researchers, 2 computer scientists, me and our postdoc, 1 lawyer, 1 sociologist, and 1 economist. And our postdoc, and I just adopted it from him, likes to do the elevator pitch of us demystifying blockchain. So this is basically the narrative of our group, and we have multiple topics in this blockchain area, and we demystify them in terms of challenging the narrative that's there. So if somebody says Ethereum is super secure, then I will come out and have an eclipse attack on the network layer. If somebody says, I don't know, stablecoins are super stable, then our economist comes out and says they're not because economic theory says this and this and that. But also, of course, not only breaking things, but also putting in perspective and having ideas how to make things better in the long run. Another topic that we are working on is consensus algorithms, in particularly Stellar, and Charmaine and Martin, who are both here today, have worked with the Stellar Beat IO people to bring an analyzer to the network. So they analyze the consensus status of the network, which is kind of cool, I think. And besides that, we also have the non-technical contributions about social and legal implications of governance of technology and through technology, as well as automated rule enforcement in the law. Today, I will focus on the resilience of peer-to-peer networks. And as I said, we broke Ethereum, so to say, on the network level, and then went on to understand IPFS. And this is what the talk today is going to be all about. Just a quick side note, and then we will get started. Why IPFS, if we are focused on blockchain? Well, first of all, IPFS is hailed as a storage solution for blockchain applications all over the place, on papers and in forum posts and Twitter and whatnot. And of course, you can store large amounts of data on chain because that's prohibitively expensive. And so the solution would be to store it somewhere else, for example, IPFS, and simply link to the hash. So that you store the hash on chain and then you know, okay, this hash belongs to that content stored in IPFS. Apart from that blockchain focus, we also are personally interested in peer-to-peer networks. So Martin's dissertation is on privacy in peer-to-peer networks, and my dissertation is on resilience and security, tying in quite nicely with the Ethereum eclipse attack. So this maybe explains, for example, the reasons why we chose IPFS as a research subject in the first place, and also our perspective with which we look at the topic. Given these perspectives, the overarching research question that we posed ourselves was if IPFS is a suitable solution for storage and blockchain applications. Because the narrative in the white paper is first and foremost censorship resistance, Web 3.0, and so on and so forth. And it's not particularly designed to be like blockchain application compatible. And so we're wondering does it live up to the expectations that people put into the network? And I would formulate a yes. But to be more precise, what we looked at in our paper and also in the subsequent works is how many and what types of node participate in the network as the first question. The idea being that if there's nobody there and there are only 10 nodes network, then it's pretty useless as a system in general. What type of nodes in terms of clients and nodes that actually participate in the DHT, for example. So think DHT is a Bitcoin, you have several nodes actually contributing resources for the health of the network, and then you have clients simply using those resources to use the system. And you need the full nodes, you need the DHT-enabled nodes in order to have a healthy system, and this is what the second part of the question is all about. Secondly, how decentralized is the network? And this is a very, very broad term, of course. We've mostly focused on decentralization on the network layer, so distribution of nodes in countries, distribution of nodes through autonomous systems, the degree distribution of nodes on the overlay, and the share of infrastructural nodes, so for example, gateway traffic, as a metric on how much is in infrastructural nodes and how much is actually coming from other people on the network. Thirdly, the question how secure and robust is IPFS against civil attacks, especially if it uses academia DHT, which has been attacked over time again, then this question simply arises. And last but not least, it's censorship resistant, but how private is my content retrieval? So how anonymous am I on the network? So to tackle these questions, we looked at the content retrieval mechanism, and this will probably not be very new for most of you, but just to share our perspective and how we approach that, and maybe then our methodology is a little bit more clear. So IPFS is a peer-to-peer storage, nothing very new, and uses Cademia for finding content. And this Cademia gives us a mapping between the data items in the network, which are labeled here as D0 to D3, and the nodes that are in the network labeled V0 to V3. So if I, for example, as a client want to get the data item D0, I will query the DHT, and in the end up with the node set V0 to V2 and V3. So this is how a normal DHT lookup works. But IPFS is a kind of different than normal traditional systems in that regard, because it combines two complementary mechanisms in parallel. It has, on the one hand, this Cademia lookup, which is very susceptible to civil attacks, for example, and at the same time broadcasts the bit swap requests to all neighbors on the overlay. And this is kind of unusual in that regard, but also has several advantages and drawbacks. The first advantage is, of course, that it's very robust against attacks because, for example, a common thing that would be possible in any DHT is an eclipse attack, so where you partition the network either into two separate halves or just separate some peers or individual peers from the rest. In terms of IPFS, this would lead to censorship or denial of service attacks. And by broadcasting bitswap requests to all neighbors, even if I'm able to eclipse individual peers, then they might still be able to find content from the peers that have that content cached that they query. So for example, if I'm connected to a gateway, then it would be very likely, since they cache content for 12 to 24 hours, that I will still be able to obtain the data I'm looking for, even though I'm eclipsed on the DHT level. And of course, this makes the whole system very, very robust, especially if you have 700 to 1,000 peers, if you're not behind the net. That's quite a large number of connections to take out in order to eclipse a single target. But while being robust, which is a pro argument, on the other hand, of course, it's not optimal in terms of performance. So if I query 700 to 1,000 neighbors, then of course, in terms of message complexity, this is not optimal. And also, as we will see later on, privacy-wise, it's also not pretty, it's also kind of problematic, but also enables research as we did, because you basically broadcast what you're searching for to all your neighbors. And if you would happen to have a node in the middle, so to say, connected to a lot of nodes in the network, then you would be able to map which peers request which content at which time. And this ties in quite nicely with the methodology that we used. So we have three distinct approaches here. The first two were in the paper that is presented at IFIT Networking and that I talked about in the talk at the conference. So some of you might already know what's coming there. And the third part is the new stuff, so to say. This is what has been happening this summer in the course of Leo's master thesis. Just quickly what's going to happen, because this is also the outline of my remaining talk. We started some basic nodes without any connection limits, just to answer the first research question. So how many and what type of nodes are on the network? The second part is crawling the DHT, which has been quite extensively worked on in the last year, to get a glimpse of the overlay, to get a node distribution through ASs and so on. And last but not least, with sniffing bit swap, we do exactly what I just told. We have a node in the middle, so to say, connected to most of the network, which sniffs what people are requesting for bit swap. And then through that, we can deduce quite a lot, as we will see. Moving to the first part. We conducted passive node measurements, and these are the same as in the IFIT networking paper in November 2019. So it's quite a while since then. And I will talk about the implications of that in a bit. We then observed an average of 40,000 connections, and you can see the resulting graph on the bottom. So we have a node that has no limits whatsoever in the IPFS configuration, and also no limits on the Ubuntu OS operating system level, just to see how many nodes connect to us. So these are all basically incoming connections that you see here. And every 30 seconds, we log what peers we have and also their capabilities in terms of protocols. And we can see that back then, 65% of nodes were DHT enabled. So they spoke the Cademia 1.0 protocol, whereas the remaining 35% were clients at the time. You can see that there were also quite the fluctuations in the number of peers, but I will talk about them in a little bit when I come to the crawling. You can also see that the number of total IDs, so the number of unique IDs that we saw, steadily rises, which may be kind of confusing at first, but it hints at the behavior that people start their IPFS nodes in a one-shot behavior. So start IPFS, download some stuff, play around, and then stop using it. Or frequently reconfigure their nodes in terms of deleting the configuration directory or losing the private key and so on. So this might be two possible explanations for this behavior. Since November 2019, quite a lot has happened. So we have seen IPFS 0.5 and IPFS 0.6, and especially regarding the DHT handling, there has been quite a lot of changes since then. Also regarding symmetric nets and so on. So we would expect the share of clients to rise. So from 35%, I would expect that maybe 40 to 45% are now clients. And we did not redo this measurement yet. I still plan to do it, but there have been other priorities, unfortunately. But yeah, I would definitely expect a rise in clients since the latest updates. And this tackles also the first research question, how many and what types of nodes are on the network? And I have to say, it looks quite promising. So there are definitely infrastructural nodes that serve as infrastructural nodes. So they are DHT enabled. They serve the network. They spend resources to keep it running, in quite a substantial number as well. And the number of clients is also quite significant. So this seems to be a quite big network, to be honest, in comparison, for example, to Bitcoin, where you only have 10,000 full nodes. Moving on to the more exciting parts, to crawling the DHT itself. To that end, I need to explain Cademia really quick, and most of you probably already know that, so I will do that in maybe not 90 seconds, but rather quickly. So this image is taken from the Cademia paper. And what you have to know is that in Cademia, node IDs are static, public, and uniformly distributed because they are a hash of a public key, at least in how IPFS uses Cademia. And node IDs can be seen as the leaves of this binary tree with the ID with only ones to the left and the ID with only zeros to the right. And depending on its own ID, a node partitions this whole binary tree into so-called buckets, which correspond to subtrees. So the first bucket corresponds to the first subtree, the second to the second subtree, and so on. And this is done based on the XOR metric. So for example, if we are this black node right here with the ID 0011, then the first bucket would contain all the nodes that differ from our ID in the first bit. So since our ID starts with 0, they start with 1. So all the IDs starting with 1 would fall into the first bucket. The second bucket contains all the IDs that differ from our own in the second bit. So they share the 0 and then they differ in the 1, and so on and so forth. So the buckets get subsequently smaller and also the closer to our ID in terms of the XOR metric. It's important to know that the buckets are size restricted. So even though I say they are responsible for the whole network, or the whole subtree, of course, not every node ID is stored in that bucket, because it would be prohibitive, especially if the first one is responsible for half of the network. But instead, they are all at the same size. So every bucket stores in IPFS at least 20 nodes. Every connection is tried to be stored in the bucket. So everything that we see on the overlay in terms of connections should be obtainable in the DHT, and should be, I will talk about the restrictions of that approach in a bit. What we now use for mapping this whole bucket structure is that since a node ID is public, static, and known, and we also know the XOR metric, how it's computed, basically everything is public. So the bucket structure of a node, I can reconstruct and I can forecast which ID will fall into which bucket if I just know the node ID of a particular node. And this is exactly what we use to crawl the network. So Gardenia has this notion of find node requests. And if I send a find node request with a specific target ID, then the node that I sent this request to will respond with its closest neighbors to this target ID in reference to the XOR metric. So what I now do is craft target IDs that specifically map into each bucket. So I craft them for the first bucket, for the second bucket, the third, and so on and so forth, until the targeted node doesn't return any new IDs to me. I brought this example, the sequence diagram. On the left, you can see our crawler, and on the right, you can see crawled node V with the node ID 1101. And to get in the first bucket, I need to send an ID that differs in the first bit. So easily enough, I have the ID with only zeros that differs in the first bit, corresponds to the first bucket, and the closest nodes that node V knows to this ID are the ones of the bucket of the target that I'm sending. So when sending this ID, I get the entirety of bucket 0 with N1, N2, and N3 back. Then I move on to the second bucket. I craft an ID that's the same in the first bit, so the 1, and then differs in the second with the 0 to get the content of the second bucket, and so on and so forth. So in the end, I repeat this process until there's no new nodes that I learn from this target that I'm crawling, which tells me that I've now basically exhausted the knowledge that this node can give me, and then move on to the next one. And what this gives us is that we, on the one hand, have nodes in networks. So we have node V as a node in the graph, and we have nodes N1 and 2 and 5 also as nodes, but also now have the edges between them. So between node V and all the other nodes that we have obtained from its buckets, we know that they share a connection on the overlay, which basically is an edge that we can now deduce from that. You may ask, why do we need yet another crawler? There are quite a lot in the literature. Well, that's basically the problem. There's a vast literature on crawlers, but there are little implementations of them. The one problem is as well that traditional Gardenia crawlers are not really applicable, because they are focusing on systems that are, I don't know, 5 to 10 years old, UDP based, and not really easily transferable. So it's easier to just write your own new crawler than use the old software if it's even obtainable. And last but not least, existing IPFS crawlers, back then there was only one, are not really optimized for performance. And this is a problem if you want to not only enumerate all the nodes, but also get an accurate snapshot of the edges. Because if you're trying to get a snapshot of the network while it's in flux, so it's changing due to churn and so on, then if your crawl takes too long, you will see artifacts of that in your measurements that will distort the results. And this is a thing that you definitely want to avoid at all costs, which is why we optimized our crawler for performance in that regard. The QR code points to the same link as the footnotes, so to the GitHub repository where we maintain our crawler, mainly handled by the other Sebastian on the author list, so my student assistant, who has been doing quite a lot of work to get that piece of academic code running and also reproducibly running on different machines, and has done quite a lot of work to make this accessible to other people. I talked about what can be learned through crawling and what cannot be learned because of the size restriction. So I said every node tries to add each connection to its local buckets, and this is definitely true. But if the bucket is full, then this attempt is futile. So these connections will not be reflected in any data structure that we can obtain from the outside. This in turn means that not every overlay connection can be observed through crawling, limiting what we can see. And I've brought an example here. So you have the overlay on the bottom in black with, again, 4 nodes, V0 to V3. And then you have what we see in the buckets in the blue and the dashed lines as V0 to V3 again. And what can happen is that, let's take the example of V0 and V3, two nodes that probably have themselves in the first bucket, so they differ in the first bit. If they establish a connection on the overlay to exchange messages, they will try to add the respective other communication partner to their buckets. But due to the space restrictions, they fail. So there's no way that these connections will ever be added. And there's, for us, no way to know that these nodes share a connection on the overlay. What happens most of the time, although, is that we have connections in one direction. So for example, between V0 and V2, we learn that they are connected through crawling of V2, but if we crawl V0, we don't learn this connection. And this is basically only due to the space restrictions in the buckets. But still, the crawl is quite useful in that regard, because as a function in DHT, we are able to enumerate all the nodes in the network. So if imagining the thing as a graph, we know that we have all the nodes, all the vertices that we can know, but we only lack knowledge of some of the edges. And for the subsequent analysis of degree distributions and resilience and how many nodes have to take out, for example, and to partition the network, this will only yield us a lower bound, which is, I think, a good metric still, and still quite useful in assessing the health of the network, because we can say we need this and any, we need to attack these and that nodes in order to take the system down, but this is only the worst case scenario. So probably it will be better in reality, or quite frankly, is pretty surely better in reality. Moving on to the results. These are again pre-0.5. And you can see here over a course of 7 days, the crawling results. Each crawl took 4 minutes on average. We did 2,400 crawls back to back in this period. And we found a total of 44,000 nodes on average per crawl, but as you can see, that fluctuates quite a bit depending on the time of day. These nodes are distinguished between all and reachable. And by that, I mean all is really all that we can see through enumerating. And reachable means these are nodes that we were able to connect to, establish a successful peer-to-peer connection on the network layer. And there's quite a discrepancy here. And this can be due to several reasons. And I think the most prominent of them is what has been addressed in 0.5 and 0.6. Namely that at the time when we were crawling for the first time, and also for the paper, nodes were broadcasting their IPs on the DHT, even though they were only local or private. So you had no way of knowing how to connect to these nodes. And that was quite a substantial share of nodes in the network with that behavior. Since 0.5, this has been addressed. So for example, if you're behind a symmetric net, then you would enter the network as a client and only enable yourself as the DHT-enabled node if you have a stable IP and port pair to the outside reported to you. So these results here are a snapshot from basically a year ago. So this is not, it has to be taken with a grain of salt. If you crawl again right now, you'll see only 20,000 nodes in the network at all that are DHT enabled. But still a lot of them are not reachable in terms of connection that we can establish. And this is still a thing where we are kind of stumped, where we are unsure where this is happening, because the latest changes in the newest versions of IPFS should basically address this problem, and we are unsure why they remain still unconnectable. I said that the share of local IPs was quite substantial, and we can see that in the geographical distribution as well. So this table is quite a lot, I know. But if you focus on the column here, local IPs, the count is 24,000. So this means that we had 24,000 nodes out of the 44 on average that only reported local and private IPs. And these nodes, if you run the crawl again, are now all gone, which is a very good sign. And also explains why we saw 44,000 nodes back then, DHT enabled, and now only see about 20,000, because these are exactly the local IP ones that are missing. Interestingly, we also see that the nodes from China dominate if you look at all nodes. But however, if you look at the nodes that we were able to connect to, then the US dominates by quite a bit. And this may hint that there may be a usage, like a one-shot usage of IPFS, or a usage of normal users, for example, because the peaks that you see here and the number of nodes in the network corresponds quite well with the time of evening in the Asian countries. So it could be, especially given that there are so many nodes from China, that people tend to spin up the IPFS per usage in the evening and then turn it down again during the night. But this is only a hypothesis, and we have no way of really knowing for sure, of course. Last but not least, I would like to talk about what has been going on this summer, because it's quite exciting. And I will say we all the time in this section, but it has to be noted that all the heavy lifting in terms of designing the systems, implementing and running them has been done by Leo, the master student, has been working on it. So please give him credit when I say we, and pass this as our own joint work, because there has been quite a lot of fiddling around in that regard. So what did we do? We basically did the same thing as in the first part, where we had a long-running node to observe the network. But this time, we still have the long-running node with no connection limit, but we modified the code so that the bit-swap messages are now logged. And this gives us a trace of bit-swap messages over the course of 5 months. And we recorded all messages that we received. So this gives us the information about which peer requested what CID at which time. And on top of that, we also resolved the recorded CIDs to respective content, so using the normal IPFS API, and build up a database of resolved CIDs, the metadata of them, MIME types, for example, links to other blocks, and so on and so forth. So quite the extensive data set, as you will see here. So we have in total over 5 months, 3 billion received bit-swap requests, which amounts to 305 gigabytes compressed traces of these requests. We have 50 gigabytes of peer lists also compressed, because we log the number of peers every 5 minutes, and roughly 350 million unique CIDs, and 305 million of those are resolved in a database that is about 51 gigabyte in size, with 450 million links between those resolved CIDs. So yeah, as you can see, just handling that amount of data to analyze it is very painful in itself. That's a very intricate endeavor to get all this stuff running. So again, Leo, well done. And also there's been a lot of nodes crashing and weird behavior and lots of pieces that have to work together. And I would want to highlight a behavior that we observed multiple times, and we have absolutely no explanation for that. And I think that may be interesting for you, and maybe you have seen that in the past. We have inexplicable connection behavior in the number of peers. So as you can see here, we have 2 virtual machines, one in the US, one in Germany. On the y-axis, you see the number of peers that they have and the time on the x-axis. And we have this very weird behavior where there's a very steep and sharp drop in connections that lasts exactly 48 hours, and then it very steeply and sharply rises back to the number where it was before. And this happens to both virtual machines. This happens sometimes even simultaneously to the virtual machines, and we have no real explanation on why that is. So we have no timeouts to the best of our knowledge in the IPFS code. There's no thing on the Ubuntu operating system level, at least as far as we know. So if you have seen that before, or have any ideas, we would be very happy for any feedback on that. But still, even during these 48-hour drops, we still received basically the same amount of bit swap messages from our neighboring peers. So we would argue that this does not render the results that we have any less useful, because you can see in the fluctuations that it's basically an unnoticed. So you cannot really notice the drop in the number of peers and the number of bit swap messages received. Okay, what can we do with this very complex measurement setup now? For example, we can see the development of messages over time. And I think this is a slide that will basically be very nice to see for most of your protocol labs. So what we can see here is the count per day of messages, bit swap messages that we received over time, starting at the end of March, going until September. Also marked are release candidates and releases of IPFS clients. And what we distinguish here is if we received a want block or a want half. And just for those of you who aren't very deep into the bitswap code, before 0.5, whenever you requested a content, you basically sent the want block to all your neighbors, and then the neighbors responded with the block itself. So the data basically, you said I want this hash, and then you got the data immediately. This had the problem that if you requested popular content, then you got the same things several times from your neighbors because there was no interchange between them. So for example, if I request the IPFS README, then it could be that to receive it 7, 9, 10 times from my neighbors, which is suboptimal, of course. So in 0.5 release candidate 1, this process was exchanged for a more inventory style, if you think of Bitcoin, way of handling things. So you would send a want half for a hash, and then the peers would respond with, okay, I have the data. And you could then subsequently connect to those peers or contact those peers where you want to download the data from, eliminating the duplication that arises through sending the data directly. And as I said, this was introduced in release candidate 1 or the last version of 0.4. I'm not really that sure, but you can see that in March, there was basically no peer using that mechanism. And by the end of September, or mid of September, we can see that the want half messages are basically now the only way how Bitswap is used, which is quite remarkable for a peer-to-peer network, in my opinion, because this shows how quickly people update their clients and how quickly updates can be rolled out to the general network, which if you compare it to Tor, for example, where it's just a nightmare, is a good sign, and also very nice for you as developers to know that things that you change are probably enrolled quite quickly. Moving on, we also used our infrastructure to deduce gateways. And this has a particular reasoning because if you remember, we still have that how decentralized is IPFS question now back of our mind. And we now have eliminated that there are centralized points in DHT, but what about the gateways? Because they translate HTTP to IPFS basically, and are very popular. And if we would find out that most of the Bitswap traffic originates from them, then of course in usability terms, this is quite nice, but of course not optimal in terms of decentralization. But the HTTP side is public, whereas the IPFS side is hidden in gateways. So you don't know the peer IDs and the structure and how they function on that side. And we send forged CIDs through the HTTP sites through the gateways, and then searched our Bitswap traces for these CIDs in order to identify the IPFS side. So they get node ID or node IDs even of the gateway that we can access through HTTP. And this then enables us to disentangle the Bitswap traffic share into gateway traffic that originates from them and normally homegrown traffic that originates from normal users. And then again, we can deduce things about how decentralized the BitSwap traffic actually is. And as you can see, it's quite good. So this is a trace from July until the beginning of August. Again, requests per second is on the y-axis and time on the x-axis. And the blue line on top is the non-gateway traffic. The red and green line on the bottom are from all gateways and then only the Cloudflare gateways. And you can see that there's quite a substantial amount of non-gateway traffic. It's very significant, significantly more than the gateway traffic. And although Cloudflare gateways are pretty popular, if you look at the charts, there's also quite a lot from other gateways as well, which is, in our opinion, a good sign for the health of the network, because it seems to be mostly homegrown IPFS users using BitSwap and not only directing the HTTP clients through the network, which is also fine in terms of usability. Still, I think gateways are a great thing for people to get involved, but in the end, you don't want to have everything routed through them. This leads me to the last point that I will address today, namely the content storage in IPFS. So I said in the beginning that we have this database of resolved CIDs due to the reason that the requested CID that we have in the trace does not reveal anything about the content itself. And we wanted to know what content people are requesting. So what are popular files and what are popular MIME types, for example. And to that end, Leo resolved 305 million CIDs that we saw to build up a really large database of these CIDs, metadata, and the links. And interestingly, this allows us to traverse this Merkle dark upwards. So normally, if you have a large file, for example, you have a root hash of the file, and then you chunk that up in multiple blocks, and the root hash points to those blocks. But there's no way of knowing if you only have the block to which root hash this belongs. And this has a very normal reason, because the same block could be used in several files. So just for deduplication reasons and to save bandwidth. So it is very reasonable to not include any link to the top layer in the bottom layer block. It's very good that this is actually oblivious to the root hashes. But sometimes you want to know, out of interest or research interest or whatever, to which root hash this block actually belongs. And this is exactly what this database allows us. It allows us to traverse the Merkle dark not only from root hash to the blocks, but also from blocks to the corresponding root hashes that refer to them. Which is kind of, which is pretty nice actually, because then you can do all kinds of analysis about the MIME types and the files stored and whatnot. Coming to an end. This brings me to the current work that we are doing and the future work that we are planning and the ideas that we have. For the immediate future, of course, the publication of the BitSwap measurements is the first and foremost point of action, because in academia, as you already know, probably you publish or you perish. So this has to be done. And I also think that it is quite interesting. For example, if you want to simulate the system, if you want to improve BitSwap, then you can use the trace as input as actual user traces, how they request data to assess the quality of your algorithm. You can use that to analyze the content that's stored, and so on and so forth. So there are many directions of future research in that BitSwap measurement study alone. Sebastian, the other Sebastian, the student helper, at the moment measuring or trying to measure BitTorrent file system, because that has seen quite a lot of attention in the past. And we were not sure how much of that is marketing and how much of that is actually the network itself. So we thought it would be interesting to crawl that and compare it to IPFS, especially since it's basically a fork. But for some reason, they have a weird security protocol mismatch. So our crawler at the moment cannot connect to BitTorrent FS nodes, which we are still investigating. Potential ideas for the future, but we are not sure if we will ever have the manpower to do that, is to gather all the software that we have now, developed in the last year, in a holistic monitoring setup. So think of Ethernodes, for example, or BitNodes or StellarBeat.io, just to assess the health of the network in terms of number of nodes, distribution, and so on and so forth, in a centralized homepage, or probably even in the backend that you have if you run your own local IPFS node in the JavaScript backend. Something like that. That would be pretty cool, but we actually have no person who can work on that right now. In terms of BitSwap, there's a possibility to improve the performance or to improve the privacy, or even both, with a variety of possible extensions that have been proposed in literature that you can assess, even design new algorithms for, which is quite interesting field of research, I would say. And last but not least, I didn't go on that in very much detail in the talk, but we found some illegal content on IPFS, namely youth pornography, that we also notified the German authorities about, the law enforcement authorities. And probably gateway nodes would want to have a mechanism of deleting CIDs and the corresponding content and not forward them as soon as they get positive knowledge that that content is illegal. Of course, that is a very delicate question because of the censorship resistance of IPFS, and also if you don't want to start like a cat and mouse game of blocking a specific CID, and then you can simply alter one bit to get another one and then repeat the process ad infinitum. That's not very desirable, but I would say that this is a very interesting and probably necessary part of the project in the future, that there should be maybe a decision on how to deal with such incidences and how to protect the gateway providers, because they reside in nation states that are that have good jurisdictions, and that makes them vulnerable against illegal content that they distribute and share to the network. With that, I want to conclude my talk. I presented the measurement-based network analysis that we did on IPFS. In total, I would say, addressing the research questions in the beginning, that IPFS is Sybil resistant, very nicely Sybil resistant, but due to that, a bit suboptimal in performance and privacy. Again, this enabled us to do a very, very interesting measurement analysis in the last half year. So this is not seen as criticism alone, but maybe just as a point on how to improve in the future. We would say it's sufficiently decentralized in terms of country, autonomous system, and node degree distribution, which is very good. Has a lot of active users, a lot of nodes participating in the DHT. And this is also our hypothesis in the end, that most nodes are operated by private individuals. And although infrastructural nodes exist, IPFS is by far not centralized, by far not, and even like compared to Bitcoin, for example, where you have these centralized mining pools, IPFS lives the dream of being still a quite decentralized network. Again, you'll find the code to our measurements, the scripts and so on here. And thank you very much.
We can start with just sort of an open jump in with questions. If it gets, just if you don't have an opening to ask your question, just type hand or question into the Zoom chat, and I'll try to, I'll step in as a facilitator.
Yeah, very interesting talk. I've got several questions, but I would like to start by the BitSwap one. Did you, like all the CIDs that you gathered, have you managed to figure out things related to popularity of content, for example? Have you done any such like investigation?
We have started the investigation. The problem is that there are some artifacts in the results that we see, so in the data that we measured, in that some peers, very few, 3 to 5 peers, request the same content, the same CID, like 1 million times.
Okay.
And that distorts the results, and this has been like the major deal breaker in getting like a real popularity distribution of the content in itself. Very shortly put, but yeah.
So you could, for example, exclude those 3 to 5 nodes out of the statistic?
Yes, we tried that as well. You can see actually in the thesis of Leo that he forwarded a week ago or something. There's like a whole section on the problem. The thing is to identify those anomalous nodes, like what is anomaly and what is actually user requests of BitSwap. And of course, if there's 1 million requests, then it's normal. It's not normal, but it's very hard to draw the line somewhere. Maybe somebody is requesting it with a script of what is normal behavior and what is artifact is kind of hard to distinguish. And this has made it difficult to have a popularity content distribution.
Okay.
Not to say that we are not trying to get that, but
Yeah, absolutely. Okay. Another question I had relates to the kind of not downtime, but the sharp drop in the number of peers for BitSwap. So the figure showed that in this case there was the US-based virtual machine that got the sharp decrease. Do you say that those kind of alternate and sometimes the EU-based one goes down? So is it a more general kind of conclusion that we can arrive at, or could it be?
We have definitely seen it on both VMs, so both Europe and US. And I remember one case of being even remotely synchronized on both machines at the same time. So yeah, I would say this is a more general conclusion that we have, but both machines use the same operating system. So this might still be one possible reason that's not related to IPFS, but rather the Ubuntu that we used. But yeah, even then I would say that since Ubuntu is such a popular operating system for servers, this is probably a thing that should be addressed in some regard, or investigated at least. And we are at the end of our rope with investigating that.
Great, thanks.
Other questions or thoughts?
In the last slide, I think that you showed about how decentralized the gateways and how what percentage of requests goes from gateways and which ones comes from other peers. Did this? I didn't get it correctly. Did this graph show how much content was served through BitSwap as compared to gateways, or did it show? Yeah, here it is. Or did it show how much content is served from like normal DHT servers as opposed to IPFS gateways?
That's actually a very interesting question to study in general. Like how much is BitSwap, how much is IPFS provided, DHT provided. No, but this graph only shows the BitSwap side. So BitSwap in terms of BitSwap traffic served by gateways.
And not only gateways, the blue one is other peers.
Yeah, exactly. The blue one is other BitSwap peers, but not DHT.
Right. Okay. Very interesting. Okay.
But you're definitely right that that's a very interesting question how they relate. So how much is actually provided through DHT requests and how much is provided through the BitSwap requests.
Yeah.
And a quick follow-up. This is not only useless bandwidth, but even control messages. And so the overall bandwidth exchanged by BitSwap, right?
This is the number of requests received, like 1/2, for example.
1/2. Okay.
I guess this is also on this question, which is if you've got a sense of how to estimate the amplification that caching on the gateways would have. So if you might expect that if the gateway has a cache, it can serve many requests out of cache. And so the traffic from gateways may actually be higher in terms of client traffic from what you observe through this side measurement of how much it's fetching. Do you have ways of estimating what that impact would be and how much of actual client traffic would be going out of gateways?
I mean, cooperating with the gateways, of course, you can easily get the cache hit, but I mean, from the outside, I mean, what we could do is feed the traffic that we see on the BitSwap side from normal peers into the gateways and see how big the cache hit ratio is, so how many requests are forwarded to the rest that we can observe and how many of them are simply answered by caching.
Right, you've got a distribution of content relative popularity through other things potentially, although it may be skewed. And then you can see how far down that popularity curve the gateways are going, and from that potentially can estimate their cache size and then model what their actual traffic rate might be if it follows the same popularity curve.
Yeah, definitely. Yeah.
I mean, just jumping in and thinking aloud as well. If I understand correctly, this plot shows does not deduplicate the messages. So if we have multiple messages for the same CID, you would get the same plot. So
No,
if
this is
you
with deduplication,
deduplicate it,
actually.
sorry, this is with deduplication.
Yeah, we have the same plot
Well, then,
without deduplication.
well, then
but
you
not
could
the
make
middle.
you could. Ah, okay, sorry. Then sorry for that. Then, but then maybe this plot is already answering the question, because there is a time to live on the cache, right? Or isn't there? I mean, at some point they would have to perhaps request it again. So if you run it for a long time, then you could at least discount the cache effects a little bit.
Right, or you at least learn what their eviction looks like and can estimate their cache size from that.
Mm-hmm. But I think the timer is refreshed, right? So if I request, for example, the IPFS README time and time again, then this will stay in the cache forever, right?
Yeah, okay, maybe you're right. So we just have to restart the whole network once, and then it's going to.
Also, like the note about filtering content is an interesting thing that we should sooner or later, I guess, like put on our agenda. So filtering offensive content and so forth.
Yeah, that's a very, it's kind of hard to assess the different sides of this question, I think, like filtering the content, because you don't want to, I mean, kind of talking a bit more political, but in Germany, for example, if you say child pornography, then anybody's like, yeah, we should block that, and there has to be a censorship, whatever. So yeah.
How did you find in the first place the content? Meaning technologically, were you just manually looking at content, or?
Mm-hmm. So we had this database of IDs. I mean, back then it was only like 50 million, I think. And then Leo looked at a random sample of text files, of images, of videos, of PDFs.
Mm-hmm.
And then this folder came up, and we were like, oof. And we sent that to the German authorities, and they were like, yeah, okay, probably.
Oh, so hold on. I see. So you're saying that you discovered it by chance, just
by
like
chance, yes.
And so you presume, like, what percent of the pages that you had would you say you looked at randomly? Because I'm just wondering what percent of the network this traffic is.
Let me think. I think it was 1,000 CIDs chosen at random for each category. So not that many. I mean, it's Leo's been doing that by hand on his own.
So he looked at all the 1,000.
Yeah.
Roughly speaking, okay, yeah. I mean, it would be interesting to know, what we should think about this issue.
And out of curiosity, what was the German authorities' reaction? Did they give any kind of recommendations or guidelines? I suspect they don't know how IPFS works or anything, or...
Not at all, no.
Did they recommend something? Did they...
I think they were mainly confused. So you have different levels of German authorities. We forwarded to the state of Berlin, and they were like, okay, what is IPFS? What is the DHT? How did you find the content? What is a folder? And they were like, okay, and I said correctly, this is like a Dropbox folder that I put on there. And so there were a lot of questions that were very, very early in the technical process. And in the end, they said, okay, we don't know how to deal with that. We didn't find anybody. But we forwarded that case to the German federal authorities. Maybe they will come back to you, which hasn't happened so far. So I guess that IPFS is just too obscure for them to deal with.
I mean, the thing is, so what, I mean, it kind of sounds a little weird, right? We're sending stuff to the police, but we are researchers and we kind of found this, and it's kind of illegal to store it. So we kind of had to report it. And we're also at the Weizenbaum Institute. We are supposed to, help the government in a broader sense to get a grips on all these kind of digital stuff. So we also saw it as an experiment if we can cooperate on this edge. I mean, again, speaking a little bit more broadly, more politically, we would like to have cool decentralized networks, but I mean, some stuff that people can do with them are just not cool. So in the very big picture, we should figure out how to deal with these kinds of things. I mean, it would be sad if a few bad actors ruin it for everybody. So maybe we can find some intelligent middle way.
Yeah.
What I find interesting, I'm not sure if this is something that's on the Protocol Labs agenda, so maybe to turn around the question, but we were able to find this because right now the privacy in IPFS is a little bit, not existing, basically. I mean, you can connect to all the nodes in the network with reasonable effort. And right now, if I don't have something in my cache, I basically ask all my neighbors. So if you really want to surveil somebody and see its, its request patterns, it's like scarily easy to do. We did, as far as I know, we don't have anything stored that's problematic from a data protection standpoint right now, but maybe I just should stop talking right now. But I mean, the challenge is there, and it's also not obvious to me how to resolve this because it comes with obvious, like with other drawbacks in terms of performance, for example, and latency. I don't know.
But I think if it's on the agenda, it's like with the Tor network. If you can speed it up, and then of course the anonymity is kind of bad, but then you can still reintroduce delays if you want to, or the same for BitSwap. You can optimize the performance and then reintroduce noise or like all these privacy enhancing things that make it at least harder for an adversary to get the privacy thing. But then it's a deliberate choice more than, okay, we broadcast to everybody and like giving, or maybe even have a spectrum of possible settings that you can have. I want more performance, I want more privacy in my IPFS node, and then choose for yourself, for example.
It's even harder to design these things when only a small fraction have opted into privacy, though.
Yeah,
versus
that's true.
it's the whole network.
That's true.
So thank you for your talk. Really appreciate it today. If you're watching on YouTube, please remember to like and subscribe and share with your friends. This was a great talk. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description. We'd also love to have you join our mailing list to receive quarterly newsletters, future talk announcements, and information on research funding opportunities from Protocol Labs. You can do this in the footer at research.protocol.ai. Our next talk is in 2 weeks, also Tuesday, October 20th at 1800 UTC from Naomi Ephraim, who is a PhD researcher at Cornell University. Her talk will be on non-malleable time lock puzzles. So thanks for joining, everyone, and I hope to see you next time.